so I hope you can see the importance of sets, the importance that sets play in our discussion here. Probabilities are functions. Probabilities are functions from F, functions from F, which is the set of all subsets of interest from omega to the unit interval. Okay, so it's a special. So a probability is a special kind of a function. It maps a set to some number between 0 and 1. Okay. Now, so when we write P of this, we read that as the probability of this. Okay. The thing that appears here is an event. In general, it is not a number. It should be a complete sentence. Okay. I know I didn't write a complete sentence, but it's the probability of this thing occurring, whatever this is, like that the world ends tomorrow, or the probability that you get an A in this class, or the probability that your dad wins the lottery, or whatever. Okay, so this is an event, and to this event, it's going to assign a number, like 85% or something. Okay, now we need to lay down some axioms before we get started. So we'll start with probability axioms or probability rules. Probability rules. Probability rules. Okay. These are just things that we need to lay down and agree on in order for probability to make sense. Okay. So first of all, first probability axiom is for any event, E sub I, the probability of that event is at least 0. Probabilities are never negative. It doesn't make any sense to talk about a negative chance of rain, right? If the chance of rain is negative 5%, well then we must be living in an alternate universe. Second is that the probability of getting some event in the sample space must be 1 or 100%. Same thing. Okay. You must get an outcome in the sample space. Probability outcome, and it turns out that probabilities of events that must occur are 100%. Okay. Events that must occur have the probability of 100%. Events that cannot occur have probability of 0. The converses of those statements are actually not true, it turns out. We won't worry about it, but yes, it turns out that just if an event has probability of 0, it doesn't necessarily mean that it cannot happen. And just because an event has a probability of 100% doesn't mean it's going to happen. But we won't worry about that. I'll save that for a measure theory-based probability course. But our final axiom here is that for disjoint events, say E1, E2, etc., E2, which means that E1 intersect E2 is the empty set, E1 intersect E3 is the empty set, and in fact EI intersect EJ is the empty set for all I and J. Meaning that they don't touch. They can't happen at the same time. Okay. They can't overlap. Like here's E1, here's E2, here's E3, here's E4, here's E5. Okay, and so forth. They can't, no pair of these can happen at the same time. If this is true, then we have this nice little nugget here. It says that the chance of the union of those guys is equal to the sum of the chances. Okay. And that kind of makes sense because you could think of this P as being paint, right? The amount of paint needed to paint the event that is the union of those. Well, how much paint do you need to paint their union? It's the same as the sum of the amounts of paint, right? I'm not a very good painter. Okay. See, if instead you had this kind of picture, this was E1 and this was E2, then the probability of the union of these is not equal to the probability of E1 plus the probability of E2, right? It's not. See? Because if I take the amount of paint that I need to paint this and add to it the amount of paint that I need to paint this, I've sort of painted too much. See that? I've painted the middle part twice. So in general, I'm going to move this way now. Ready? 1, 2, 3, go. In general, the probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. Okay? You just have to subtract off that part that you intersected there. Also, the probability of A union B is less or equal to the probability of A plus the probability of B. This is called countable subadditivity. Actually, more generally, the probability of, if I take the union of any events, not necessarily disjoint, it turns out that the chance of that union is going to be less or equal to the sum of those probabilities because they might be overlapping. Okay? You can see that, you know, if I drop some events in here, maybe they overlap. Okay, here's some events. You know, the probability of their union is, you know, it's all of this stuff. But if I added up the individual probabilities, this one, you know, chance of that, plus the chance of that, plus the chance of that, plus the chance of that, I'm counting some areas twice. Okay, and in fact, this could exceed 1. This could exceed 1. This cannot exceed 1. Okay, the sum of a bunch of probabilities could in fact be larger than 1, but that doesn't violate axiom 2. Axiom 2 says that the chance of the entire sample space is 1. Okay. All right. So, any questions? Any answers? Okay. So now let's do let's do one more thing here. This will be our rule for complements. Rule for complements. This says that you have to be nice to each other. Okay. It says that if I have any event, say A, then the probability of A is 1 minus the probability of A complement. Or another way to say that, you could say, you know, just simple algebra here. The probability of A complement is 1 minus the probability of A. You know, for example, if A is the event that it is raining, then the probability of A complement is 1 minus the chance of A, right? That makes sense.